Whenever mathematicians see a new and helpful definition, a natural question that comes to mind is whether it's possible to create analogous versions of existing theory. Let's illustrate a few such results. We begin with the sum rule, whose derivative version is straightforward. The detachment version is slightly trickier and requires posing some conditions on the involved functions and wrapping the right-hand side with the sine function. Next, let's consider the product rule, whose differential calculus version is as follows. It involves merely the function's pointwise values and derivatives. To formulate its trend analog, it may be helpful first to illustrate the different possible values of the trend of the product, given the trend of each function separately. When we do it, it's possible to see emerging patterns and observe that we need the function's sines and another definition, namely the function's sign continuity, to better separate cases. While the semi-discrete product rule resembles and extends its differential counterpart, including application to non-differentiable and discontinuous functions, it's more complex than it may initially appear. Lagrange's theorem in differential calculus states that within an interval of a differentiable function, there is a point where the instantaneous rate equals the average rate. A similar principle for trends suggests that within an interval of a continuous and detachable function, for any chosen threshold between the n values, there is a point where the function meets this threshold, and its instantaneous trend matches the overall trend. As seen in this illustration, applying the differential calculus version of the mean value theorem can be limited, for example, due to cost points. The integral mean value theorem does not require differentiability and posits a point where the function's value multiplied by the interval length equals the total interval's integral. A similar mean value theorem exists for detachable functions. Selecting various thresholds shows at least one point where the threshold is met, and the local trend equals the interval's global trend. This is a straightforward extension of both Lagrange's and Bolzano's theorem. Inspired by Grothendieck's wisdom,
one should never try to prove anything that is not almost obvious.
The straightforward nature of our new findings does not lessen their elegance or potential. Instead, it enhances the beauty of the mathematical journey we share. The sum, product, and mean value statements we discussed based on the detachment are examples of other analysis results derived from derivatives and integrals. This table summarizes analogous calculus results based on derivative, integrals, and detachments. Some results, like Green's theorem, involve integrals and detachments in their novel version. Your car's dashboard demonstrates calculus in action. Mileage is akin to the integral of the distance traveled, while the speedometer depicts the derivative of the distance over time. These physical tools approximate abstract concepts. The gear sticks, indicating travel direction, often align with the derivative sign. Forward, reverse, and stationary match positive, negative, and zero derivatives. However, it isn't necessary to compute the derivative to assess its sign. As Aristotle and Newton suggested, nature doesn't waste effort. Hence, we may not need to calculate rates to determine the instantaneous trend of change. If you want to learn more about the theory and applications of semi-discrete calculus, feel free to check out this book called Introduction to Semi-Discrete Calculus, available online.
As we continue our journey, let's explore an intriguing question in our next segment. Could an AI have orchestrated the processes of discovery and invention? Stay tuned.